how do you find the intersection point for two lines in 3D? That's what I'm going to do. And so this isn't really a physics question, but I'm a physicist and I like to approach this from a physics perspective, and I think that helps us understand it. So I'm going to solve a problem. I made up a problem for two lines, but I'm going to describe a line in 3D using physics of a moving particle. And then I'm also going to make a 3D model of it in Python. So we're going to get a lot of stuff here, and it's going to be a ton of fun. I'm super excited, even though I don't exactly know what I'm doing. I'm going to just do it anyway. So this is the definition of the velocity for a particle that has a constant velocity. So you imagine a particle in space right here. It's moving along with some velocity. We can represent the definition of velocity as the change in position, where we use position as the vector r with respect to time. So if I multiply both sides by delta t, I get delta r equals v delta t. Now, if I say the change in r, it's going to start at r0 at t equals 0. So that means the change in time, I'm just going to write as t, right? Because this is t minus 0. And the change in r, I'm going to write as delta r equals the r at some position minus the initial r. And that way I can get it in the form that everyone is going to be happy with. So now if I put this along with that, I get r. I'm going to add r0 to both sides, equals r0 plus v delta t. This is a three-dimensional line, because if you think about r, let's say r is equal to x, y, z, then this is actually three equations, because I have this, the components of this side of the equation have to be equal to the components of that side. Oh, I left off, that should just be t, because remember I said t0 is 0. So I can write this as x equals x0 plus vxt, y equals y0 plus vyt, z equals z0 plus vzt. And so those are my three equations, and these are actually parametric equations. Parametric equations. Because think of it this way, if I have some particular velocity and starting position, x0 and vx are constants, y0 and vy, these are constants. And if I want to move along the line, any different place on the line, I just let t be some different value, and that will pick a location on that line. I'm going to model this and come back, and because I think if we do this in Python, it's going to help. And then we can go back and find the intersection between two lines. But let's just model this first. Now, typically what you're going to see this in a math class, they would write this as x equals x0 plus at, y equals y0 plus bt, z equals z0 plus ct. I mean, that's the same thing. I like thinking of it in terms of the x and y, z and v components of velocity. It's just cooler that way, don't you think? Okay, now wait, there is one other thing here, and that's these symmetric versions of the equations. If I solve this for t, I get, I'm going to subtract x0 from both sides. I get t equals x minus x0 over a, right? Because I can subtract that from both sides and divide by a. And then I can do this one too. T equals y minus y0 over b. And then t equals z minus z0 over c. Now, I'm just showing you this because you see this a lot, and you'll see this line written as, since these are all equal to t, these are all equal to each other. So I have x minus x0 over a equals y minus y0 over b equals z minus z0 over c. And you can't even see that because I moved the paper down, and I apologize. Okay, so the important thing is if you see it in this form, then you should be able to extrapolate out a point vector form. And the point vector form is this, right? Because it says where does it start and what's the velocity. So in this, I have the point P0, let's call it, I guess we'd call it R0, would be x0, y0, z0, and then the the velocity would be v is a, b, c. So let's start with a point in space. I'm just going to pick it when I get there. Actually, I'll pick it now. Let's start with a point, and we're going to use time and map out the line in 3D in ClosesScript VPython. And I'm going to give you the code. Okay, so here I have, let's say R0 equals 2, -1, 1. And then v is going to be equal to, it's hard to make up numbers sometimes, you know. Let's say -1, 3, 2. And in physics, these would have units, but that's fine. And so what I'm going to do is to make this a point, give it this velocity, and move it in Python. And so how do you move things in Python? Well, I'm going to pick a delta t, because I have to plot it, right? I can't plot every single t. I have to pick something. So I'm going to pick delta t is 0.01. Why not? I'm just going to pick that. And then if I start with R0, I can find the next point in space. I can say let's just call it R1 is going to be equal to R0 plus v delta t. That's v. That's not. So I can multiply my velocity by that little time interval, add it to my old position, I can find my new thing. I could find the next position, R2, would be R1 plus v delta t. So I can just take that v delta t and add it to the next one. And I could do this, R3 equals, and so forth. Now, there is another way I can do it. I could also say R3 equals R0 plus vt, where I just multiply it by the actual time and always start from the beginning. Now, I'm going to do it this way for now. They all have a time associated with them. So each one is be t1 is t0 plus delta t. t2 equals t1 plus delta t. And so that's my parameter t. Okay, so let's go over to Python and let's map this out and draw a three-dimensional line. Now, the hard thing about this in Python on paper is that this is a two-dimensional surface. So if I have this as, see, x cross y, this is x, that's y, and that's z, it's really hard to start mapping things out. But it's not so hard to do it in Python. So I will give you the code, but let's switch over to here. So this is ClosesScript VPython. I'm using trinket.io. You can also use, let me put a code right here. So I'm using trinket.io, https trinket.io. Why am I putting that on there? I don't know. But the other place is is it colon? Yeah. I don't know why I had mental lapse there. ClosesScript.org. So those are two places that have this Python built into the web page, and it has vectors and three-dimensional objects built in, which is super nice. So let's just start right here and call this ball1 equals sphere. I'm going to use the position I gave it over here in the paper. So I'm going to say position is equal to vector 2, -1, 1. Now, there's something else I want to do is to give it a radius. How big is that ball going to be? And I'm going to say 0.2. I don't know if that's going to be too big. And I'll give it a color too. Color equals color.yellow. And then let's just run this. Actually, I should say this. Let's say this. R0 equals vector 2, -1, 1. And then down here, I'm going to say this is just equal to. So in Python, in ClosesScript VPython, we have these objects built in. Sphere is a built-in object, and it has a couple parameters that we can give it. We can give it the position, the radius, the color, and things like that. So if I run this, let's see what happens. There's my ball. It's at a location, the origin somewhere right here in the middle. So this is x equals 2, y equals -1, and z is out of the page, so this would be towards us. Now I can actually right-click and rotate this around. It is in 3 dimensions, see? I can zoom in, zoom out too, so that's kind of cool. Now, there's one other thing I want to do. I want to say make trail equals true. This means when I move that ball along, it's going to leave behind a trail, and that will be our line, the equation of our line. There's another way to do it too, but I think this will work. Okay, so now I'm going to say the velocity, v is equal to vector, what did I say it was? -1, 3, 2. 3, 2. So I want to move this ball and animate it drawing a line. I could do it quickly, but I want to animate it. So what I'm going to do is to say t equals 0, dt equals 0.01. That's how much I'm going to step by. Because it's not drawing every line, right? I'm actually jumping, but it'll look nice. Now I will say while t is less than 3, so this will do it up till parameter t equals 3. Rate, let's do 100, even though that might be a little bit. So rate is a component of, let me make this a little bit bigger. Rate is a component of GlowScript that says, okay, I'm going to animate the motion of this thing and how fast you want that animation to run. So if this rate 100 says that I don't want GlowScript to do more than 100 calculations every second. So the higher your rate, the faster the thing's going to run. If I put rate as 1, it would just do 1 calculation every second. Okay, so we can change it if we want to. So the first thing I'm going to do is to, I'll calculate the new position of the ball. Actually, I'm going to call this just R. I shouldn't do that, but yeah, so it's the first one. In Python, I can just change that value. I don't even actually need the first value. Okay, let me do it like this. R0, and then let's say R equals R0. There. Okay, so the first thing I'm going to do is to update the position of that ball. Or I'm going to do it this, you could do it one step. I'm going to say R equals R plus V times dt. So this says take the old position, the previous value of R, which this first loop is going to be R0, and add this V times delta t to it. So this is not an algebraic equation. This is a make equal to equation. So this says take whatever that is and make that the new variable. So it will now become R1. The next time it will become R3, R2, and R3, and so forth. So we don't have to have all those different variables. Now I'm going to actually draw that sphere. So I'm going to say ball1.pos equals R, and that moved it. Now one other thing I want to do is to update time. So I'm going to say t equals t plus dt. And that should be it. And let's run this and see what happens. There it goes. There's my line in 3D. And I could go on forever if I wanted to. But you see, it is indeed a line in 3 dimensions. I can rotate it around. Now, what if I want to have that's my initial point right there. Let's put a point there. Let's say P1 equals sphere, position equals R0, radius equals 0.002, and let's just not put a color, that'll be white. That'll show you where we started. This is the location where t is equal to 0. And as t increases, my parameter moves along this line right there, where that ball is, up until t equals 3. So this is t equals 0, t equals 1 is 1/3 of the way, and so forth. So I can find any location in there. If I want to move another point, watch this, I could say, let's do it after I draw the line, and make this a little bit faster, because I'm that impatient. So 5 times as fast. Now I'm going to put a point, let's say t equals 1.8. So if I want to calculate the location of that, I can say P2, I have a new point, is sphere. It's going to be R0, a position equals R0 plus V times T. Is that P2? Right. And that's where it's going to be. Now I need to give it a radius of 0.2, and let's give it a color of cyan. And now let's run that. So there it is. See, I put the point right there. That's at t equals 1.8. I can move that along wherever I want, and that's where it is. Now what if I want to have more values this way? I just run this for a longer time. I could run this till t is equal to 5, and it'll go longer that way. It goes on for infinity, but I can't draw it to infinity. And then there's my point's still there, see? Okay, let's put this back at 3. What if I want to do The other way, well, I can just do this. I can copy this and make another loop, let's say right there. What I'm going to do is move the ball back to the starting location. So I'm going to say ball1.pos equals r0. And I'm going to go and let's set t back equal to 0. T equals 0. And I'm going to move back in time. I'm going to say while t is greater than -3, and I'm going to say dt is -0.01. So this is kind of a weird thing. This is like moving back in time, right? If I move back in time, each time my time is going to get smaller and smaller and smaller, but I'm moving in the opposite direction. I think this will work. Let's see. So there, drew the first way, jumped back down there, and it went the other way. T, no it didn't. While t is greater than, okay, I think the problem is, let's put this, I think it changed the value of r0. Let's see, print r0. So r0 was 2, -1, 1. And did, okay. So P1 is right there. Why is it going? It's not jumping backwards. See, right here, it should move the ball back. I just have it go there and that right back. But ball1.pos equals r0. Let's do this. Print ball1.pos. I told you I didn't know what I was doing. Huh. I must be doing something wrong. So while t is set t equals 0, while t is greater than -3, r equals, oh, I didn't reset r, that's why. Okay, I reset the position of the ball, but I didn't reset r, so r equals r0. Okay, now it's gonna work. I don't need to print that anymore. So I'm gonna move to the end of that thing, and then I'm gonna jump back to the center and then start over again, going in the opposite direction. There. Excellent. So now I extended the line. These have negative values. And in fact, I can go down here and say where I put this ball, t equals, where did I do that? Right here. Right here. So let's say t equals -1.8. Now it'll be in the negative direction. And that's the parameter. There. Right down there. See, there it is. Oh, you know what? You can't say because my freaking face is covering it up. Let's turn that off. There. So there's the negative value down there. Okay. So this is t equals 0. That's negative t equals -1.8. And this is my equation line in 3 dimensions. And that's how you do it. Okay. And so using this point vector formula, I think is the best. Because that's like initial position and velocity. Okay, now let's go back over to the paper. We're going to solve a problem that hopefully works out, but maybe doesn't. And that's finding the intersection point of 2 lines. Okay, so switching back over here to paper, I picked some problems. I picked some values that may or may not work. Okay, so here's what I have. Do these 2 lines intersect? I'm going to write them in point vector formula. So line 1, I'm going to call this R10, that's the initial point. It's going to be equal to 1, -1, 3. And then at the end, I'll show you how I got this value so that it'd work. V1 is the velocity for that one, and it's going to be equal to 3, -1, 1. And I'm going to write these in symmetric form too, just to make everyone happy. And then my other point is R20 is the vector, I'm looking for it, here it is, -2, 0, 2. And if they don't intersect, they don't intersect. And my velocity V2 is going to be equal to 1, 2, 3. So if I want to write this in parametric form, I would just write the following. So remember, I'm going to write it out as R equals R1 equals R10 plus V1t. And this is the position at t equals 0. So if I write this as just the x components, I get x1 equals x10 plus vxt. But as a number, I know x10 and I know vx, right? So that would be x1 equals x10, which is 1, plus 3t. And then I can do the same thing for y1, and this is y1 because it's line 1. y1, a lot of times I'll just put that as x, y, and z, but I'm a little bit more meticulous than that. So y1 is going to be -1 minus t, and then z1 is going to be equal to 3 plus t. That's my equation 1 in parametric form. If I want to get that in symmetric form, I'm going to solve all these for t. So this would be x1 minus 1 over 3 equals y1 plus 1 over -1. So it'd be t. No, that's right. And then solve this for t, I get z1 minus 3 over 1. That's my symmetric form, which I think is stupid. But that's, it's not my role to make a judgment, right? Okay, now let's write this one the same way. I'm going to write this as x2. I like writing that equation. So r2 equals r20 plus v2t. Now, I don't want to use t because the parameters in this one are going to be different than that one. So I'm actually going to call this something else. Let's call this u. So now I get x2 equals x20, which is -2. v2x is 1, so plus u. y2 equals 0 plus 2u, so it's just going to be 2u. And then z2 equals 2 plus 3u. So then here are my two equations in parametric form. Now, do these lines intersect? If they intersect, then this x has to be equal to that x. At the same time, this y is equal to that y. At the same time, this z is equal to that z. They have the same point in space. They have to. They don't have to have the same t and u, but they have to have the same x, y, and z. So that means I get the following three equations by just matching these two together. I can say this has to be equal to that. So 1 plus 3t equals -2 plus u. And then I can set this one equal to that. I get -1 minus t equals 2u. And then this one to that. I get 3 plus t equals 2 plus 3u. And I hopefully picked out some stuff that works out fine, but if it doesn't, I'm going to blame myself. So here I have three equations, three variables. No, I have two variables. Variables. So I can take the two of these equations and solve for u and t, and then plug that u and t into the third equation and see if it works. If it doesn't work, they don't intersect. If it does work, it does intersect. Okay, so I'm going to switch to a new sheet of paper so I have plenty of room, and then I'm going to draw both of these lines. Okay, so let's right here. So I'm going to take let's write out the three equations. 1 plus 3t equals -2 plus u. -1 minus t. And you can use any variables you want for these parameters. I'm just using t and u because it just made sense at the time. Equals 2u. And then 3 plus t equals 2 plus 3u. So I'm going to solve this one for u. No, I'm going to solve this one for t. So if I do that, I'm going to add t to both sides and subtract 2u from both sides. So I get t equals -1 minus 2u. Is that right? So if I add that to both sides, yeah. Okay. Now I'm going to plug that in up here everywhere I see t. So that becomes 1 plus 3 times negative 1 minus 2u equals negative 2 plus u. So now I have an equation with just u, and I can solve that. So let's say 1 plus minus 3 minus 6u equals negative 2 plus u. I'm going to add 6u to both sides. I have 1 minus 3 is negative 2. I'm going to add 2 to both sides, plus 2 equals plus 6 equals 7u. U equals 0. You don't equal 0. You don't equal 0. U equals 0. Okay. So now I can use that to find t. So if I go up here, u equals 0, t equals negative 1 minus 2 times 0 equals negative 1. So I have the pair u equals 0, t equals negative 1. That's the parameter on the two lines where they intersect. If they do intersect, which they may actually not. So I'm going to take this third equation, and I'm going to plug in these variables up there. So I'm going to plug these in up here. So I get 3 plus t is negative 1, equals, question mark, I don't know, 2 plus 0, right, because 3. So I get 2 equals 2, check, intersect. Now, where do they intersect? They intersect at t equals negative 1 or u equals 0. You can use whichever equation you want. So over here, I'm going to plug in u equals 0. If I plug in u equals 0, I get x2 equals negative 2, y2 equals 0, z2 equals 2. That's the point that I picked. Oh, you know what? I did this backwards. I actually picked another point. I just realized I crossed that one out, and I picked a different point. Oh well. So this point I picked is the intersection point. I still think we learned something. Okay, I'm going to show you how to find the other point that I meant to use here. Now, if I go over here and say t equals, what was it, negative 1, then I can put in my values here, and I get x1 equals 1 minus 3, so negative 2. y1 equals 1 minus negative 1, which is 0. Negative 1 minus negative 1, right? And then z1 equals 3 minus 1, which is 2. Same point. So we do have an intersection. Okay, let's map out these things. I'm going to use actually not a moving sphere. I'm going to use cylinders. So let's jump back over here to Python and map this out. I'm going to turn off the camera because that was a mistake before. Okay, so here's all my code. I'm just going to delete everything. No. I'm going to save this. Let's put this as def of 3D line parametric, even though I didn't even use the parametric. And I'm going to save that. I'm going to give you the link to that code. Okay, now I'm going to make a new program. It's too big, let's see. Let's make this smaller so I can do this. New trinket glow script. Okay, now I need let's make it bigger again. So let's put in my 2 points. I'm going to use the values I had before. I'm not gonna make these spheres. I'm going to say R1 0 equals, just like I did before, vector 1 negative 1 3. I'm going to do v1 equals vector 3 negative 1 1. Now I'm going to do the other one. R2 0 is equal to vector negative 2 0 negative 2 negative 2 0 2, and v2 equals vector 1 2 3. Okay, I want to plot this line. Okay, and I'm going to have, let's go ahead and I'll use t and u. No, I don't even need to do that. Okay, so what I'm going to do is to use a cylinder. So a cylinder is like a line. If I make the radius of that cylinder very skinny, it will work. In Python, cylinder has 2 parameters. So let's call this L1 equals cylinder. It has the position, which is the vector location of one end of that. I'm moving my hands around, and you can't even see it. Let me turn on the camera. I feel like I want to use my hands. Okay. So let's use, and I'll turn it off if it gets in the way again. So the position of the end of the cylinder is going to be R10 equals R10. And then the next parameter is axis. That's the vector from the beginning of the cylinder to the end of the cylinder. So that's going to be axis equals V1. It's just a vector. And I'm going to need to change that in a little bit, but that's fine. And then I need the radius. Let's do 0.1. And the color, let's make this one yellow. And let's run that. See what it looks like. Okay, and you can't see it because my face is in the way. Okay, let's see if I can move this up here. There. So there is my cylinder. It's off to the side and a little short. So what if I want to make it longer? I can just increase the length of this V1. Let's just do, I can just multiply that by 2, which essentially goes up to 2t. This just goes to t equals 1, essentially. And then there it's longer. Okay. Now I'm going to go, if I want to make it go in the opposite direction too, I can just make another cylinder with the vector in the opposite direction, but let's just not deal with that right now. Okay, let's make my second line. So L2 is cylinder. Position is R20. Axis is equal to 2. I'll go ahead and multiply that by 2. Radius is 0.01. And let's make it cyan. Color equals color dot cyan, and run it. And there you go. So do they intersect? Well, you can't really tell because I didn't draw them long enough. It looks like I'm going to extend both of them, and then we can see if they intersect, and I'm going to put a point there. Okay, so I'm actually going to draw another line to line 1. Let's say L1 negative is equal to cylinder. Position equals the same thing, R10. Axis equals negative 2 times V1. So now I'll be moving in the opposite direction. I'll be pointing in the opposite direction. Same radius equals 0. I can't type sometimes. 0.1. Same color. Equals color dot yellow. And then run that. And you can see they do indeed intersect at that point, like I said. And then I can move this one back. I'm just going to copy this. And then paste it and go back over here. Change this to -2. And I'm going to give it a different name. You don't have to, but I'm going to. L2N and run that. Boom, intersecting lines. And then we calculated that point. I'm going to go ahead and plot that point. So let's say ball 1 equals sphere. Position equals the thing I calculated from over here was -2, 0, 2. Vector -2, 0, 2. And let's put the radius of 0.2 just so you can see it and run it. And there you go. There's your intersection point. And you can rotate this around, and yes, they do intersect in real life. Okay. Now, how did I see this if you just pick 2 random lines, they're probably not going to intersect, right? So how did I do this? Well, what I did was I picked this first line, L1, starting up here. And then I used my parameter of t as -1 to jump back over here and find that point. And then I wanted to, and I did, I wanted to pick a point down here, so I went back down to -1 this way and found that point. And so let me show you that other point that I picked. Let's see if it actually worked. Ball 2 equals sphere. I'll just type in the vector. Position equals, because I had in my notes here, I had vector 4, -2, 4. And then let's put a radius of 0.2. And so that should be on the cyan line. It should be. Yeah, no, I put it on the yellow line. That's up there. Huh. Okay. That's weird. Why I messed up then? Okay, well, you can see how you would indeed do that, though. So there you go. That's what a 3-dimensional parametric line is, And that's how to find intersecting lines, by solving 2 equations, 2 unknowns, and then plugging into a third equation to see if it still works. Can you do that in Python? You could. And this is different than 2 balls colliding, right? Because if you have 2 balls colliding, they have to have the same parameter too. They have to have the same time. So they can start at different places at different times, but they'd have to have the same x, y, z, and time. Otherwise, their trails just cross, and that's the 2 different things. So that's 3D lines from a physicist's perspective. Hope you find that useful. I'll include the code for this and the previous one down below, and you're welcome to play with them as much as you want, and you should.